So again, this is something you are probably aware of from last year. This is 1-6. Operations and compositions of functions. So first, starting off with operations. So if you have f of x and g of x, they're two functions, with intersecting domains, then for all x values in the intersection, the sum, product, difference, and quotient of f and g are new functions, and you can find them by doing the operations on them. So I like to give the official definition just because I feel like it's just for clarity. So let f and g be two functions with intersecting domains. Then, for all x values, in the intersection, the sum, product, difference, and quotient of f and g are new functions and then they're given as follows. So then there's this, if you have the sum, that is f plus g of x, which is f of x plus g of x. You have the product, which is f times g of x, which can be found by multiplying f of x times g of x. And you have the difference, f minus g of x, which is f of x minus g of x. And the quotient, which this one I need a little more space. We have f over g of x, which can be found by taking f of x and dividing by g of x. And when you do that, you end up with a domain restriction because g of x in this case cannot equal 0. Okay, so that is what is going on when you do these function operations. And then I'm going to give some examples of how you would do that. So that I like to give the technical explanation just for the why, like and what's actually happening. So that's what this part is. And then we're going to have some examples. So we're given f of x.
This is an example?
Yes. And we're going to use these functions for all four operations. F of x equals x squared plus 4x. And then I have that g of x equals square root of x plus 2. And h of x equals 3x minus 5. All right, so those are the three functions we're going to use for the examples. The first example is f plus g of x. So that means we take the f function, x squared plus 4x, and add the g function to it. So g is the square root of x plus 2. Okay, so then simplify if you can, but in this case, there's nothing to simplify. The only other thing is, because the instructions would have been find each function and its domain. So there's the function, because we can't simplify it any, but we also need the domain. So the domain for the f function is all real numbers, but the domain for the g function is not. We can't do the square root of 0. I mean, anything less than 0, right? Because we're not going to graph imaginary numbers on a coordinate plane. So the square root of x plus 2 has to be greater than or equal to 0. So if we square it, then we have that x plus, okay, I'm sorry. We just wanted what's underneath. So x plus 2, I mean, it's the same, really. If you square it, then you're at this step. I just meant to take whatever's under the radical needs to be greater than or equal to 0, because we can do the square root of 0, but nothing smaller than that. So then x has to be greater than or equal to negative 2. So if we take that, and that's our only domain restriction, that means that the domain starts at negative 2, and that's included, and then it goes to infinity. Alright, so that's it for the sum. And we're going to do the difference, f minus g. So f minus g of x. We start the same way with the f function, because that's what came first in our notation. X squared plus 4x. And then we're going to subtract the g function. So we want to use parentheses because we don't know what's going in there. And then the square root of x plus 2. Okay, so our parentheses didn't really do anything because there was just one single piece in there. I guess we don't really need them. You could write it again, but there we go. And then there's nothing we can really do with that. I wrote the wrong one. It was supposed to be h. Oh well, we'll just do it with g. That's fine. Again, we have the same domain restriction. All real numbers. And then this one has to be x is greater than or equal to negative 2. So we end up with the same domain. This would have been a better example if I would have done the one I had written down on my paper. But it's alright, it still works. The only thing about this was f minus h of x, the way I intended it to be, we would have two terms, and so we would have to distribute the subtraction into both terms. That's all you'd have to watch out for there. Check both the functions for restrictions on the domain, and that's it. So number 3 is f times h of x. So we start with f, which is x squared plus 4x. But this time we're multiplying it by the h function, which is 3x minus 5. Oops. So putting both of these sets in parentheses, because it's the f function times the h function. So we're going to FOIL it or double distribute, whichever way you like to say that. They mean the same thing. And I'm assuming you guys know how to do that. So I'm just going to go through it. So we have x squared times 3x, 3x to the third. And then we get negative 5x squared, positive 12x squared, and negative 20x. Then we multiplied it out here. Combine the like terms in the middle. So 3x to the third plus 7x squared minus 20x. That's simplified as far, I mean, we could factor an x out, I suppose. Doesn't really matter. And then state the domain. So are there any domain restrictions happening? You can look either here at our result, our product, or at the two beginning ones. And nowhere there is a domain restriction. If there was a domain restriction in either F or H, there would also be a restriction in its product. But since there's not, it's from negative infinity to infinity, or you can write all real numbers. Either way is fine. So then the last one is,
How do you find the domain restriction? Yeah.
well, we have the f function is x squared, so it's a quadratic. So the domain of a quadratic is going to be all real numbers. And then 3x minus 5 is a linear function. So the domain is all real numbers.
Okay.
But the square root, because the square root parent function is kind of like that. So it's from 0 to infinity. All right, so then on the quotient, we're going to do h over f. So h over f of x. The h function is on top. So that's 3x minus 5. And that's over the f function of x squared plus 4x. So again, it's still f and h. Neither one of those has a domain restriction on its own. However, as a quotient, we can't have 0 in the denominator. So that becomes the domain restriction here. Whenever you're dealing with division, it doesn't matter that neither one of them individually have a restriction. We know that the denominator cannot equal 0. So x squared plus 4x cannot equal 0. So we have to find what values would make that true. Yeah. So then we factor out the x, and we have x plus 4 cannot equal 0. So that means that x cannot equal 0, and negative 4 cannot equal 0. No, I didn't write that right. X cannot equal 0, and x cannot equal negative 4.
Oh, you just forgot the x part.
All right, so if we have two domain restrictions, when we write this, when we write the domain, that means we're going to have two unions in the domain. Okay? So if we start with the domain, it's going to start at negative infinity and go on until the smaller value, which is negative 4. It cannot be negative 4, so there's a break. And then union, with as soon as you get past negative 4, you can start your graph again. So there's just a hole there. And then that's going to go until 0, where there's another break, so you have a union. And then from 0 to infinity. So that would be the domain.
Isn't the U like you say or? Or do you say
Union?
You say union? Oh, I thought you said like the U represents or.
Is this free now? Oh, yes.
You're reading it?
Yeah, okay.
I was
Sure, I mean, it means the same thing.
Okay, I didn't know.
The technical is union,
Okay, it's like when you were reading.
but that is kind of what it, yeah, so the graph exists in this interval, or in this interval, or in this interval. Yeah, or and would work there too. It just depends on how you're talking about it. Oh. All right, so that is operations on functions. And the next part is compositions of functions. There is more, yes. Compositions. This is when we take the composition of functions. F with function g is defined by f of g of x. So f of g of x, which actually this should be like that, f of g of x, or it could be written as f of g of x. It's the same thing.
It's inside.
Yes, it's a little open dot. So like if it closed dot would be f times g. Composition is f of g. So it's like a little o in there. That's just the notation. Or the way that you're probably used to seeing it is this way. Same thing. Just different notations. So an important note about the domain is the composition f of g of x inherits the domain of g of x. It's not always the one that's labeled g of x. It's because the g came second in the way I wrote it. So that's the one you need to, it'll match the domain of the second function, the one that is being put inside of the first function. And then there's something else we'll add to that in a minute. I forgot where it was, so we'll find it. Once we get there, I'll see it. So we're just going to do some examples of compositions. So if you're given that f of x is x squared plus 1, and g of x is x minus 4. Find the compositions and give their domains. So we're going to find the compositions and give their domains. So first we're going to do f of g of x. So this would be the f function. And then inside the f function, we're putting the g of x function everywhere there is an x in the f. Alright, so if we start by writing the f function, because that comes first in either case, we're not going to write the x as really being a blank there. Squared plus 1, so there is the f function with no x in it. And we're going to take the g function and plug it in because that's what's happening in the notation. So that's x minus 4.
They put it in.
Yeah, you put it inside where the x was for the first function. And then we're going to evaluate that, or simplify that. Sorry, not evaluate. X minus 4 squared. We end up with x squared minus 8x plus 16. And then there's the plus 1 on the end.
We'll just combine.
We'll combine the like terms, yeah. X squared minus 8x plus 17 is f of g of x. So then the domain for this function is just a quadratic, so it's all real numbers. There's nothing happening there, and that matches the g. The domain of the g function is all real numbers. So it's from negative infinity to infinity, or all real numbers. So next up is g of f. G of f of x. So now the g function is coming first. G, and then inside the g function where there's an x, we put the f function. So we start by writing g. So it starts with an x, so we have a blank. And then minus 4. And then plug the f function into it, x squared plus 1. And then we simplify. Alright, so in this the parentheses aren't doing anything, so this is just going to be x squared minus 3. The domain of the f function, which is the one that's going inside, is all real numbers, and this also matches all real numbers. So the domain is negative infinity to infinity. And then we're also going to evaluate this one for f of g of 2. So f of g of 2. Well, since we already have done f of g of x, we don't need to redo the composition f of g because we already have it. It's right here. So we'll just use that, but instead of x's, it's a 2 because this was f of g of x. This is f of g of 2. So we just turn all the x's into 2's. So we end up with 2 squared minus 8 times 2 plus 17. And then we end up getting 5. So if you're evaluating either a function or a composition, you're just getting a single numerical answer because there's no x. Since there's no x in your answer. And then I have one more example with new functions. So now we have f of x is 1 over x plus 1. So those were the super basic examples. Now there's a rational expression in here. So g of x is going to be x squared minus 9. Again, we're going to find f of g and g of f and state their domains. So f of g of x, since it starts with f, I start by writing f. And then there's a blank plus 1, where the x was. Inside the blank, I put the g function, x squared minus 9. So those parentheses aren't really doing anything. I'm going to rewrite this as 1 over x squared minus 8. All right, so since the g function came second in my notation, I was going to follow the domain for that, right? That was what the note at the top said. So I would look at g of x and it's x squared minus 9. That's quadratic. That's all real numbers. However, we put it in the denominator. So now you have to make sure it doesn't equal 0. So what I said, the note at the top isn't a rule all the time. It's like unless you put it somewhere where it can't be, where it has a restriction. So here, that cannot equal 0. So x squared minus 8 cannot equal 0. So that means that x squared cannot equal 8. So x cannot equal the square root of 8, plus or minus. So it can't be the positive one or the negative one. And square root of 8, we can simplify that. So x cannot equal plus or minus 2 square root 2. Since we have a positive and a negative, that means we're going to have 2 breaks in the domain, 2 unions when we write it. So the domain is from negative infinity to negative 2 square root 2, not including that value, in union with negative 2 square root 2, all the way to positive 2 square root 2, not including the values. Jump over that value. And then from 2 square root 2 all the way to infinity. So we have 2 values in the domain restriction, and there are 2 gaps in the domain, which makes sense. So a super rough sketch real quick of a parabola in the coordinate plane, just to do a quick explanation here on the domain restrictions. So if it looked like this, it's saying there's a restriction at negative 2 square root 2 and positive 2. So wherever that is, we'll just put it right there. When x is this, and when x is this, there's 3 sections. It could be anywhere over here. Any of these x values has an acceptable y value. Any of these it's fine. Any of these, it's fine. It just cannot be those two exact points,
Like
which
all
is
those?
why there's the domain restrictions. All right, so then the last example is doing g of f of the same one. G of f of x. This time we're starting with g, so we have blank squared minus 9. There's the g function with no x. Put in the f function, 1 over x plus 1. And then simplify if we can. But you can't really, so we're just going to rewrite it. So we square this, then we end up with 1 in the numerator, and then x plus 1 in the denominator, minus 9. And we do the same thing, because we can't have a 0 in the denominator, so x plus 1 quantity squared cannot equal 0, because the domain cannot equal 0. I mean, the denominator cannot equal 0. So if we do a square root, we end up with x plus 1 cannot equal 0. So x cannot equal negative 1. So now there's only one single domain restriction. So when we write the domain, there's only going to be one union. So domain is from negative infinity to negative 1, and then in union with negative 1 to infinity.
So the number of g is dependent on the number of domain restrictions? Okay.